So it starts with one of the basic questions that many of you have asked, which is how do you compare or choose between array and a linked list representation? Okay, I've received one question. You can key in your questions till I'll take a few minutes to introduce the content of today's theme. Okay, I've received one question from Kshitija. I'll answer that in a short while. Okay, comparison of array versus linked list implementation. So here I'll drop some ideas, okay, and give you some analytical methods to choose between these two very important representations, and we'll do it both theoretically and you can also test it in practice. What are the ways we do it? We have to basically use time and space complexity. Okay, so the slide has some a table with lots of entries. What I will do is I will explain some of the entries so that you can appreciate and complete the processing for the remaining part of the table. So I'll move on to the next slide. Something is missing out here. Just a minute. So the next bullet on the first slide says that we will be doing certain applications today. You feel free to ask me other applications if you have during the question answer session. But what I will do is, so you observe that I have chosen random, or very different applications to illustrate the data structures used in solving problems. A very well-known problem is balanced parenthesis. I find it useful. This is to process HTML documents of a certain kind. Expression evaluation is also a well-known problem which is solved using data structures. Sparse polynomial manipulation I'm going to take up in a short while. And there are a long list. I may or may not be able to do arithmetic with long positive integers, but I can give you tips on how to solve it. Okay, so before I formally begin, I'll take up the only question that I have received from Kshitija, and the person is saying that they are using C language to implement heterogeneous linked list. What pointer we will use? So here is Kshitija the answer to your question, and to all those who are only using C, I'll give you a generic answer. All of it will not work, but much of it will work. So observe that in my notes I have used this word class. So class is in C++, and the equivalent in C, I'm sure you know, is struct. So if you replace my class keyword in most of my implementations with a struct, it will work for a linked list, right? If you write, for example, struct node instead of class node which I have given, and define the two value and the pointer field, something like int val, depending on what you want to store in the list, and struct node star next. This is how an element of a linked list is created. So I've just replaced class by a struct. What exactly we have done is we have created a new data type called node, which is comprised of two compartments, one which has an int and the other is a pointer to elements of the kind of node. So this is a pointer. So the first thing is replacing class by a struct. Most of the program will go through. However, there are no equivalents of many things in C. So for example, those which you will have to rewrite with lot of extra effort and will not directly translate are, for example, you will have to write, so there is no equivalent of public, private, which I keep using. Everything by default in C is public. Okay, these are missing. They translate to everything being public. You don't have to use the keyword, but the implication is, the meaning is that of public. Similarly, I'm not writing here, operator overloading, template functions, all these facilities are not available in C. We will have to keep writing separate functions. We have to keep using the functional notation and not the operator notation. For example, what does it translate to in terms of writing of code? We have to spend too much effort. I said yesterday that I can create a polynomial and I can write P1 plus P2 in C++. What will it be in C? It will be something like add, okay, poly, comma, poly. You have to call it like this. Okay, so there is a huge syntactic difference. The meaning underneath is the same, but it makes a lot of difference to the user in terms of coding in a language which is away from the language of the application. Okay, so this is what is known as an overloaded operator. So these features, for example, are there in C++, but not there in C. Otherwise, whatever I am doing, their equivalent will have to be written in a C-like manner. Okay, so having said this, I would still urge you, once you are done with your examination needs, if you want to have a good career in computer programming in the field of computer science, please do make efforts to learn C++ and you will enjoy for sure the benefits that you will accrue out of programming in this language. I'll just check if there are any more questions before I move on to the topic. Okay, Ashwarya is still saying no audio. Most sites are saying it's okay. So I guess I'll have to continue. Okay, so with this explanation that every C++ program, you know the language C++, right, and the meaning of C++, it means all features of C and some extra features, the plus plus. Okay, so I was basically concentrating on the extra features, which is what I was telling you in the previous slide, where you have a lot more control on creating and designing R classes. Okay, so let me move away and let me try and give you a feel of what I am going to do today by first picking up. I'll initiate from here and then I'll go back to my slides. The first thing that you would like to do is examine various alternate schemes or if you want to call it designs for choosing a data structure. What I'm going to do is not exhaustive, but it covers the basic ground which determines how to use this. So with this background, I would like to move away and go to my slide. Basically go to slide number 2, okay, which is trying to explain something. So this is the context in which I will be working. We are going to look at time complexity and space complexity. I hope you are familiar with these terms when you analyze any piece of code or algorithm. Okay, I have used two terms which may or may not be very standard, so I'll sort of explain them. One is called the forward traversal of any data structure. I'll define it as it comes. So forward traversal is starting from one end and going right all the way to the last element of the list. A backward traversal does the inverse. Okay. The last one bullet in the slide says both the traversals are non-destructive, which means that they do not change the content of the data structure. So I'll explain one table in great detail, okay, and then we can move on to the other ones. So look at the first table. This is talking about time complexity, and the theme is a linked list. Okay, I'm going to draw here and show it to you a little bit. Let me read the columns. I will not do all, but I'll do some. The first column, which is the linked list, gives you some idea about what is this linked list characterized by. So the first row says it has a pointer to the first element. Okay? A linked list may have indefinite number of elements, but I have only one way to access the list, which is by a pointer to the first element. Everything is inside the list otherwise. I've slightly changed the standard and said, okay, I'll give you one more pointer which always points to the last element in the list. So I have 2 pointers now, first and last. The third one says I'll have a circular list. There is no end in that. I'll draw and tell you, and then we will talk about of having a single pointer to the last element in the list. The last one talks about a doubly linked list, okay, which I'll only notionally do here, and I keep a pointer to both the first and the last. You can see that they are structurally somewhat different. Sometimes there are more pointers, sometimes the structure changes, sometimes there are one or more links. Now let me explain a row as I go along. The subsequent columns are what an operation. Suppose you want to insert into a linked list at the head. So I want to insert a new element at the beginning of the list. Insert tail says I want to insert at the end of the list. Insert any says I want to insert it at some position. Maybe it's a sorted list. I want to find out where the new element should go, decided by the value of the element, and I put it in that place. So insert any is neither head nor tail, but by some other criteria the element will go and sit in the link. There are 2 delete operations. One to delete the first element in the list, one to delete the last element in the list, and the next delete is to delete a particular element. For example, I can say delete the element with value 25. Okay, then I have to look for 25 and then I have to delete the element. Many more operations are possible. I've skipped a whole lot of them, but I've given you a way. I've given you 2 operations if I want to display the list front to back or from back to front. The entries in these elements are the cost in terms of the size of the list, which is n. I have assumed n to be the size of the list now, and everything is given in terms of n. Observe that I've used this big O notation. I'm assuming familiarity. If someone doesn't have, you can ask me. Big O of 1 means it's a constant operation, constant time operation, which means this operation does not depend on the number of elements in the list. Okay. So with this background, I'm going to take up, let's say, the third and the fourth rows of the table, and I'll skip the others for you to figure it out. So what I'm going to take up? I'm going to take up a circular list with a pointer to the last element of the list, and I'm going to examine some of these operations of insert, delete, forward and backward. So now I'll go back to my page and I'll try and see. So I'm going to examine a circular list with a pointer to the last element, or also you can call it the rear. Okay, so let's draw one such list. So I don't know how many elements are there. So this is a circular list. There are some values which I'll ignore for the moment. The list has n elements. N could be any number. The dots mean there are enough elements in between. Okay. So this field that I've left empty is the value field, and this is what makes the list circular. If I assume this to be the last element, I have only pointer to this. So this is the pointer to the list. This is supposedly the last element. Now for this kind of a list, we are going to ask these questions. How much time would I require to insert an element at the head of the list, at the front? So clearly if I put some numbers, let's say 5, 3, this is 21, then 21 is the last element in this circular list, and the front of the list or the first element which come in must be 5. And suppose I want to insert a new element which is 50 into this circular list. So what am I supposed to do to insert 50? So I first create a box with the value 50, and I will not connect it to anything. Let it stand wherever it is. In order to make it the head of the list, this is how my structure should look after appropriate changes are done. So the last element remains 21. The first element has become 50, and therefore this should point to this. And my list still points to 21, because this is the last element which was there earlier, continues to be the last element, the point. If you agree with me that this should be the correct picture after inserting an element at the beginning of the list, tells us that the number of changes which are required are the cost for acquiring a box and putting a value 50. I'm labeling it as 1. Some effort will have to be taken. Setting up the pointer of 50 to the earlier head of the list, which is 2. I have to populate this part correctly. And I have to change the next pointer of 21, which was 5, to a new thing, which is the new element. Nothing else changes. So since this operation requires 3 pointer manipulations only, independent of the number of elements in the list, we say that this cost is O of 1. So O of 1 means insert at the head is an operation which is constant time operation. I don't know how many of you have seen such a thing, so I am going to explain one more, which is insert at the tail of or insert at the rear end of the same circular list. Where is insert at the end? I'll copy the same list which had just been created after the insert. The list has element 50 at the front right now, followed by the old front, which is 5, and then it goes all the way to the last element, which is 21, and the next of 21 is 50, and the circular list points to the last element, 21. Now suppose I say insert at the rear, and insert what? Let's say I want to insert the value 10 at the end of the list. So if I want to do that, my correct picture now should be some part of the list will remain unchanged. This is 5. I go all the way to 21. Okay, now I want to add something at the rear. So this was my rear. My rear should point to something else. So where should I put this new element 10? After 21 or before 21? Okay, so that's important. Now since you are inserting at the rear, I'll take the stand that I'll add it after 21. So here is how 10 gets added after 21. The successor of 10 becomes, being circular, the element 50. And since I've inserted at the end of the queue, this becomes my new pointer. So once I know pictorially what I have to do, writing piece of code is not difficult at all. So once again you observe that there are some changes. First is to get this box and put a value. Next is to change the content of the next element of 21. So this pointer has changed. Then I have changed the next element of 10, which has become the earlier one. And also I have changed the value of pointer. So 4 operations are required, each of which are constant time, and therefore this is also O of 1. Let me go back to the table and see. Okay, so you observe in the circular list, I'm saying here both head and tail are O of 1, and that is precisely the reason. Okay, so now I'm going to pick up something. Suppose you want to delete an element at the rear end of the queue. So I'm looking at I'm skipping a few columns and I'm going to the red mark O of n, whose column head is delete the rear element of the queue. Okay. Now you can see why this is O of n. Okay. So let me get you a feel by going back to my picture and seeing why it is not constant time operation. So let's go back and look at this structure again. Okay, so this is the new list. As you can see, PTR is pointing to 10, which is presently the rear end of the list. The front happens to be 50, and here we are saying please delete the element which has the value 10, which means what we want after the operation has been successfully completed is this list where the last element has been deleted. Okay. So now observe the problems. In order to do this deletion, what was earlier was basically this 21 was pointing to this element 10, Okay, so this was, I'll put a dotted line. This is after the proper change, but the earlier picture was this. And of course 10 was pointing to the end of the list, so it was like this. These structures have been changed. So why is the operation not a cheap operation? The problem is this. In order to delete the element 10, which is what we are trying to do, we need to know who is the predecessor element of 10. So I need to know this box which has the value 21. But observe, there is no connection in the previous picture. When I give you the pointer 10, you cannot get the pointer of 21, the address of 21. The only way you can reach 21 is to start from 10, look at the next element 50, look at the next element 5, keep going, the next element 21, and after 21 I see 10. So I know I have completed the cycle. So I have to go round the list all the way before I detect the previous element of the rear element. And this is why this operation, deleting the rear, is an expensive operation. You have to run down the list and thereby incur a cost of traversing the entire list. So this is O of n. So let me go back to the document. So I leave it for you to see. It may or may not be obvious that a forward traversal is O of n. I must visit, in other words, every element once before I can tell you the elements in the list. But if you want to know a backward reversal, which means the last element followed by the next to last element, followed by the previous to last element, and so on, it's not going to be easy. The last element you can figure out immediately, but to figure out the previous to last element, you have to go around the list once. You pay one n cost to figure out who is my next or previous to last element. But since you do not know which is last, you don't know which is the second last element. You have to go once again round the list to figure out the second last element. And therefore, you observe the logic says that by traversing the list backward without using any extra pointers or any other extra information requires you to traverse the list n square times. So I'll only talk about a few in the doubly linked case. I'll draw it over here. So I'm now looking at doubly linked list. I am on slide 2 and I'm going to explain some entries and not all. It should be clear that if a singly linked list you can insert and delete with O of 1. Clearly an extra link field cannot make it worse. It will be as good as the previous one. So clearly both the inserts at the head and at the tail will be O of 1. We don't have to worry about it. Inserting at any position. So for example, if I say insert this value in the sorted order, I have to run the list, run down the list, figure out where it should occur and then place it. So O of n is mandatory. Worst case, I may have to look down at the entire list before placing a new element into the list. So insert has not improved even though we have gone all the way from a single pointer to a linear list, to a single pointer to a circular list, to a single pointer to two pointers to a doubly linked list. Okay, so somebody has asked something. I'll take that question a little later. So I'm going to explain this a little bit. So look at delete any. Okay. So where has the doubly linked list scored? It seems to have improved the traversal backward to O of n. It's not quadratic, not O of n squared. Look at the last column. The only fellow who seems to do both traversals with equal ease by looking at every element once. Delete any. I have said it could be O of 1, it could be O of n. So I should explain that when I go to my paper. Okay. And I have said that deleting both the head and rear are very fast. It has O of 1. So it looks like if you are typically trying to figure out whether I should use a linked list, okay, in the form of for an application, and you want the operations of insertion, deletions and traversals to be quick, then looks like you can choose a doubly linked list with both pointers to first and last. It's a general principle. Don't take it as a gospel truth. It may change depending on the actual application. Okay, so I'll go back to this piece, explain what is a doubly linked list. They are very popular in many applications, typically in operating systems if you want to know. So doubly linked list. As the name says, if you are talking about doubly linked lists, the word double says there should be two linked fields. So let me show you a doubly linked list with, let's say, some elements, some prime numbers, let's say. How will it look like? So and I have said it has two pointers. If I want to draw what I have written in the last row of my table earlier, first I will draw the doubly linked list. It is not circular, however. So I'll draw these. Since there are two linked fields, the data is in the middle and I have two linked fields surrounding it. It is what I have written. So what are these two blanks? These are the two linked fields. So who is the next element to 13? It is 17. So the next to 13 is 17 by my collection. 19 follows 17. So this field, the next field takes care of it. From 19 I go to 23. So this takes care of it. And from 23 I go to 29. So this field takes care of it. What is there in the first field? This is also a linked field. The first link is 0. Who is the end of 29? There is no other. So 29 has no follower. 13 has no predecessor. Who is the previous element of 17? That happens to be 13. So these are the links. Who is the previous element of 23? So that is 19. Who is the previous element of 29? So that happens to be 23. So now observe that the structure is like this. There is a value out here, the next field is here, and this is to the previous. And since I have kept two pointers, this is a pointer to the front of the list, doubly linked list, and this is a pointer to the rear of the doubly linked list, end of the doubly. Now you can see why is it so fast to do inserts and deletes here. Because you have both the links, deleting any element is very easy. If I want to delete this element, I know who precedes it, and that happens to be 17. I know who succeeds 19, which happens to be 23. So I can short circuit this by making 23 the successor of 17, and all the pointers are there with me, making 17 the predecessor of 23, which is also available. Okay. So therefore it turns out in most operations in doubly linked list are O of 1 or constant time. So why have I said that deletion of any element could be either O of n or O of 1? With a small separate stand, if we want to find an element and then delete it, suppose I say delete 17 from this list, then I have to first keep searching for delete, identify it, and once I sit at delete, I can delete it immediately. However, finding may take order of 1, order of n. But suppose I say, I give you this value and I say, please delete the node which is at 19. Suppose I say, delete this node. I give you this pointer and say, delete this. This can be done in O of 1 because I know both its predecessor and successor. Whereas in the case of a single linked list, even if I told you delete 19 and you remove the backward links, I cannot do it in O of 1. Because I have to traverse the list from the beginning, identify the predecessor element, and then I know what should be the next field of 17 in order to delete 9. So identifying the predecessor is O of n, even if I know the value that has to be deleted in case of a singly linked list. Whereas in doubly linked list, if you know what is to be deleted, it is O of 1. If you want to search and delete, then it is O of n. O of n is for finding. Observe that since I have kept 2 pointers over here, I can do a backward traversal of the list by taking the rear pointer and chasing the backward links. So I first take rear display 29, take the previous element from the left field display 23, take the left pointer, chase it and give 19 and so on. And okay, so this is the power of a doubly linked list. So I'll stop doubly linked lists. Essentially I am saying that there is too much of detail that one has to figure out, but decide a data structure, how many pointers, for example front and rear, 2 were there, how many linked fields, what should you put over there, but most importantly, what are your primary operations? Can I speed up the primary operations by choosing the right data structure? Okay, so this is the theme under which I have tried and explained to you. Okay, so now I'm using the mouse pointer. So if you have figured out, I have done this doubly linked list. I have sort of explained the various entries over here, and I have told you that this looks very competing if you are working it for a general application. For specific applications, we may choose something different than what I have told you here. Let's move on. So what I am going to do now is to very quickly run down this question many of you have asked, arrays and linked lists, and this is some quick explanation as to between a linked list and an array for implementing a stack, what could you choose and why? First, remember that array can be chosen only if you have some idea about the maximum number of elements in your collection which will ever go onto the stack. So typically to create an array, you need to block so many memory locations, and therefore creating an array, the first very basic operation, int a100, int x20, depending on what you want to do, requires an effort proportional to the size of the collection that you want to create, something like that. A linked list, because you initialize, you also want to initialize the array, therefore you want to spend O of n time. In a linked list, all I do is create an empty list, so it's O of 1. I don't have an element, I have nothing to fill it in. Okay, but in array, I already have prepared an array of so much size, I have initialized with some reasonable values, so I have put up a decent effort. If you look at the rest of it, you observe there is hardly any difference, despite using a linked list, okay, which is not direct access. The times for the various operations are quite competitive. It is very comparable. The only thing which is not comparable between an array and a linked list is that in case of linked list, the is full, is the stack full, is an operation which does not really require implementation, because the stack is full only in some sense when the heap is full. Okay, so it's not very relevant and it's easily done, whereas for arrays you have to do it because your elements can easily exceed the size of the initial population that you would have chosen. Now if you look at the linked list, otherwise if you look at the array and linked list, it looks like there is hardly any difference between when I choose a stack or an array. Okay, so this is indeed a great advantage. Come down to a queue. I've given you some possible implementations of a queue on the same slide. Observe again that I can use a circular queue. The last row, I can use a linked queue with 2 pointers, non-circular, or I can use a circular array. Again, you observe that the first and the third are very competitive. The operations are same. So between an array and a circular array linked list, there is hardly any difference. The operations are equally fast. The only thing is a circular array will have a size limitation and it will take some time to create and initialize, whereas in case of a linked list queue, I do not invest too much time while creating it, but as the size grows, the queue will grow. Okay, let's see if I can take some questions from you before I move on. Yes, so now my problems are starting, problem solving session. So before that, let me see what are the questions that have come up in the meanwhile. Okay, so there is another question and she's saying, nope, it's a girl. The question is, how do we reference all the elements in a one-dimensional array? So I am using reference as a normal array, okay, and not as an array of references, which is not allowed in C++. So I'm writing the question here and trying and answering it. Question is, how do we reference all elements in a 1D array? Okay, since I have not probably fully understood the question, I'll attempt an answer. But if you want to chip in more as to exactly what your question is, please feel free to do so. So how do we create an array? So I may create an array as int a100. Often when you use an array, you do not want to use the array up to its full size. Even though I have created 100 elements, I may like to use only a part of it, say 20 elements, 30 elements. So if you do in C++, this is probably what we will do. I'm using another int variable called size, and I will read like this. In C++, this means that please give me the value of the number of elements of the array you want for this run. Okay, so I do this, and then depending on what you like, I can set up a local loop which starts from 0. So that's how arrays are indexed. Go up to size, which is one less than the physical size, the last index. I do something like I++, and then I write into these locations the value that I read. Similarly, if you wanted to write out all the values, I could have done cout less than a of I. So I'm trying to answer the question, how do I refer? So this way I have referred to all the elements that I have used in this collection. If you gave size equals 50, then I have only used the array from index 0 to 49 or A0 to A49. Okay, and all the elements are being read by the above loop. If by all elements you meant 100, then I would have changed this loop by replacing size by 100, and I would have read all the elements whether they are ready or not. Reading the elements of an array, all I have to do is I have to set up an index and decide how many I want to read, where I want to read, and by choosing appropriate values of this variable I, you can read all the elements. If I did, for example, int I equal to 0, I less than size, and I plus equal to 2, then I will read the elements A0, then A2, then A4, or all the even locations of the array, right? If you wanted to read all the odd locations of the array, I could have started like this and I would have done it. So the point is, depending on what you want to do, you can set up these parameters appropriately to read all elements of the array or any pattern of elements that you want, odd, even, or whatever else you want to read. So reading an element of an array is like this, but this is not reading an array of references. In case that was the question, the answer is you cannot define an array of references in C++. We can't we use comma on the place of semicolon in the initialization of array and size? Okay, I'm not very sure if I understood the question. Can we use comma in the place of semicolon in the initialization of array and size? Okay, so let me try and see whether I have understood the question properly. So what I did last time is I did something like int a of 100, and this is what I wanted to do. Okay, so I've got a lot of questions now. Maybe I'll take them up. Sir, can't we use comma in the place of semicolon in the initialization of the array and size? So here you have to use a comma, for example. So that I don't know what exactly if you meant this. Otherwise, if you are willing to repeat and there is no difference on the quality of the program really, you can use this. So declarations must end with a semicolon and they are comma separated. You can use anything comma separated provided the type is same. Okay, so you can define comma separated variables, arrays or scalars provided they define they are of the same type. Okay. For example, I can write int a comma b comma c comma d 10 comma e equal to 5, f equal to 0. All of these are fine. It ends with a semicolon. All of these are comma separate. I hope I've carried the meaning to you. Now I think there were more questions, so let me quickly review them. How will we enter into a circular linked list? Yes, good question. Right? Because a circular linked list is a circle. You have to decide how to enter. So the point is, the designer of the list decides how you want to enter. And in some sense, so let me explain this question. This is important, particularly if you're seeing it for the first time. So how do we enter? This was the question. A circular list. So C code is not important here. First, let's see how a circular list will develop, and we have to take a decision where you want it to point to, the first element or the last element. Okay, let us say I have given you a last element solution. Let's say we want to point to the first element of the list, if that makes sense. Okay, and the circular list does not have to be circular while writing my text. It can be a normal list. So we essentially will do something like list equal to 0. Let's say this means a list which is empty. So what does it mean? That I have a place for a circular list and I put null or 0 inside it. So it does not point to anything, and therefore this is an empty list. So let's add an element. Let's say I'll add an element 1 to list. I add or insert. Yeah, I insert 1 to this list. So list, of course, is the only way to enter the list, which is the list which I'm going to point now. Now you have actually added an element. So I have a value 1 to it. Since it's the first element, I want list to point to this, so he points to it. However, since it's a circular list, where does this point to? This points to itself. If this list is having the value 100 or 1000, which is the address of the first element, this is 1000, then 1000 is also stored here. Only then you will get this picture. And 1 is the value. Okay. So this is a circular list with the pointer which is list pointing to the first element of the list whose value is 1. This is easy because only one element was added. Let me add the value 51 now to this list. Okay, so what do I want to do? I want to have this list 1. 1 points to 51 because I want to add this. The list, I want to point to the first element of the list. First element is still 1. So this is what I want to point to. But this is circular, so then 51 points to the next element, which is 1. So what I have tried to do, I have tried to show you pictorially that I can have a circular list in which the pointer from outside is pointing to the first element, and depending on what you are doing, inserting, deleting, I'll keep pointing to the first element. So how do you enter a circular linked list? Is basically, that is your decision. This is where you have to decide. Some people keep it to the first element, some people keep it to the last element of the list, which means the element which was just added the previous time. So the first element will always be 1. If you are changing to the last element, this will not change, but now the pointer will go to 51 and so on. You have to manipulate. You can't use both. It either points to the first element of the circular list or to the last. The trickier part is, suppose I reach an element like this, a list like this, and I say delete the element in the queue, sorry, the list. After deletion, you will have to create an empty list. All that you have to manipulate through your program. So conceptually, a circular list is no different than a regular list. Only thing is there is no end. There is no node which has a 0 value in the next queue. Every pointer is pointing to some element, okay, and that's how it is gone. An academic question, I don't want you to waste your time. What would you think this link list will look like, which is also circular. Okay, so I have drawn, I would say, a hypothetical figure in which there is a circular list, but the circular list does not contain all the elements. The back link is going somewhere in the middle of the list. So notionally it is a circular list, but such lists are of rarely any use in any application, because you would like to cover all the elements in the circular list and not a small part of it. Typically, there may be strange applications where this is. Okay, let's see the rundown. Can we create a linked list with variable number of values in each node? Okay, so this is the next question. So the next question is, can we create a linked list? And I'll interpret his question to mean a diagram like this is one value. Okay, let's say this is 20, this is 5 and 2.0. This points to another element. This is what your friend wants to know. Let's say 2.5, character small a, and a value 25, and like this pointing. The fact that this element has only one value, which is 20. This element has two values, so the structure of the field is different. This has three values. He can even ask something different. He can say, I want two linked fields. So I don't necessarily have to have different value fields. For example, I can say, can I have something like this, where there are two linked fields and one value, let's say a string CS101 or something. So this is the spirit of the question. I've tried to explain what he wants, and then now we have to answer it. So variable number of fields in a node typically in both C and C++ are not allowed, and this for a very simple reason. Remember that this itself, you take this box, this is a data type. Whether you use a struct or you use a class, this is a data type that a user has introduced, which has one value, okay, and one address. So now you have to specify what is the type of this address. So the small box that I have created, I have to define is an address of what. If I define that this is an address of an entity like this, then only it may work. But then all of them should be of the same type. You cannot have variable number. So basically this type of the address, once decided, cannot be changed, the address type. Typically we say the address is of a similar kind of a structure. Therefore I have a linked list with uniform structure. If I say the address of this is a different structure like this, it will work for once, but the next time all these boxes will have same kind of address. If you have understood what I am trying to say, that it all depends on the data type that you introduce while creating these boxes. And once you define what is the address you want to put in here, you give a type declaration that is enforced on all instances of such things that you do. So if this points to something like this, next time it cannot point to unless you keep doing these things. So this is not a generalizable solution. You may create 2-3 such different entities and link them together, but in generally you cannot create a linked list of arbitrary number of elements, but these things are going around. There may be applications where it is required, but then you need some different mechanism for. Somebody is asking what is the hashing technique. Please hold on. In module 2, which I am going to do from next week sometime or the following week, I don't remember, from QEEE only, there I will do hashing in full glory, so you don't have to worry about this. Okay, can we display the elements in a linked list in reverse order? Yes, you can easily do that. Actually, I have given you 2 examples. I have given you many examples in my linked list design where you can do that. And again, I'll say it very quickly. If you are introducing your linked list type, you can do something called, you can add a reversing of a list as part of a function. So I'll say, okay, list.reverse will reverse my elements. So what do I do? Of course, I need to, it will be nice to have and access to the last element of the queue if you want to do it fast. Reversing is not an issue. The issue is, can I do it fast? Can I do it quickly? Okay. So for doing it quickly, you'll have to spend some time and effort. You have to create the data structure so that you can reverse this fast. For example, in a doubly linked list, you can reverse it very, very easily. There is one more question come up from Sahul. How to enter an element in the sorted header two-way circular linked list? Okay, so I'll explain through example. Okay, programming of course should be your job. So what he's saying is that suppose I have a two-way circular linked list. So by two-way, I'm not very sure. I'm hoping he means a doubly linked list. Is that what you want, Sahul? Is it a doubly linked list? Sorted header two-way circular linked list. I don't know what you mean. Yes, okay, good. So he clarifies he wants a doubly linked list. Okay. So to short my discussion, I will use this notation to create a doubly linked list. Okay, and he also wants it to be circular. Okay. So basically this element connection goes here. Okay. Let me, without loss of generality, assume that my doubly linked circular list, this is how I'll describe this structure, two linked fields with pointer to the first. I have only one pointer. Okay, and you observe that in doubly linked list I don't need two pointers. So if I take the first element and take the previous value, I'll get anyway the end of the list because it's doubly connected. Okay, so what he's saying is, so let me put some value. Suppose it is sorted in ascending order. So let's say this is 20, this is 51. There are two linked fields which I'm not drawing. Suppose this is 62 and this is 115. So I have this. Now it is sorted, as you can see. They are sorted in ascending order. And manually I am trying to work out with all of you. Suppose I wanted to insert the element 53 into the list. You can do anything. Even you can insert, for example, the value 2, which is the first of the list. You can insert the value. All of this will go through a similar process. 291. Anything can be inserted. I'm going to pick up and insert in the middle of the list, which is 53. So what do? I have the element, the pointer to the first element in the list. So I will pick it up, 20. I compare 20 with 53. So I know that I have to go down because this is 20 smaller. So I move and go to 51 and compare it with 53. Even now 51 is smaller. So I move ahead, I compare 50 with 62. And now I know that 53 is less than 62, so it must be inserted in between. Okay, so now let me do it. So I'll first, of course, my 53 is well placed. Okay, so here is 53. Both the linked fields, let me draw it more clearly. So here is 53. I have not connected it. I am about to connect it to this sorted linked list, but I have already reached this place 62, where I know I have to insert to make the list once again become sorted. So what do? I take the successor of 51 and I put it to 53, so my red mark. So I'm going to change one end of this link and saying no, 62 is not the successor of 51 but the new element 53. Once I do this, I also know 53's predecessor should be 51. So pardon the bad drawing. So 53's left link, previous link goes to 51. I have changed some pointers. I have changed one pointer, I have changed two pointers. 62's previous was happening to be 51. I change that and say no, your previous is 53. And the next of 53 now becomes 62, so I change this. I have changed these two pointers completely. Okay. No change before 51, no change after 62, but 4 pointer manipulations between 51 and 62. So in constant time, after you have identified the place of insertion, I can insert. Basically 4 pointer operations. But you have to search, you have to find where, which may take O of n. So overall it's O of n to find and insert. So this is the advantage that you have in a doubly linked list. And once you know where to insert, I have complete connection both backward and forward, which allows me to always insert or delete in constant operations. I hope I have clarified this. So the alcove for it will not be difficult. Exactly what I said I will do. Okay. So I can write list.insert, which is circular list sorted. So what I am doing is basically comparing. Let's say I have pointer. Yeah, I'm comparing pointer arrow val, and this is my new element. Let's say new. Okay, this is what my basic comparison is. If it is equal to new, the value already exists. I may not do anything. I am done. If the pointer arrow val happens to be less than this, and it's ascending order, then I move down. I do ptr equal to ptr arrow next, and I go to the next element. If it is greater, then I know where to insert. So I will move down. In this case, I will prepare to insert once I have done this. This is what I have done. So look at a value of the current place, compare it with the incoming value. Depending on whether it is equal to first case or less or greater, I'll take 3 different actions. So I have to identify for which greater than is important. For less than, I move down the list. This is not the right place. For equality, I have identified, but there is nothing to do. The element is already there. I just move on. So the algorithm will be as good as this. The 2 questions which I have. One is how do you swap the nodes of a linked list, and the second one is about how to write a declaration. And the third one somebody had asked, I didn't really answer, is what is the advantage of using a header node in a linked list? Okay, so I'll answer these 3. So I'll take the first question, which is about declarations. So the question is, okay, suppose somebody writes like this. I think the person has asked something similar but different. I'm going to explain it with this example. How do I read this declaration, and how does a compiler interpret, and how do we as human beings interpret? Okay. So the first note that the declarations comprise of entities like this. They are all comma separated. So there are 4 declarations which are happening in this single statement. You don't have to do it this way if you don't want to, but if you do, then still we should have an answer. So here is the first declaration. This is how it will be read. Int is a common thing, and this is star p1. How do you read this? I told you earlier. First read the name, which is p1. So I will write it as, and also read it as p1 is, to the left of it is star, a pointer to int. Okay. Or in other words, the type of p1 because of this declaration is nothing but int star. The second declaration, this is where the comma comes, and I think your friend typically is asking this question, is int p2. So this will be interpreted as p2 is an integer, or type of p2 is just int. Similarly, star star p3 is yet another declaration, and the type of p3 is, by virtue of what I have been telling you, is nothing but int star star. So int is common, is setting out here. So each declaration you read, attach it to the type, and that's how it is read. In other words, if you want to create 2 pointers to integers, then you must do this. Otherwise, p2 will become an integer. I hope it answers. Each entity is separate. The star connects to the element and not to the type. Okay. So even if I wrote instead of this int star p1 comma p2, it is only p1 who becomes int star and not p2. Okay, so this is how you read a series of declarations, comma separated, pick up the name along with the string that precedes it and then attach it and figure out what is the type declaration. So now I have talked about how to swap the elements of a linked list. So if you are trying to create an arbitrary linked list and trying to make it sorted, then this question is very relevant. How to swap, which means interchange, two arbitrary elements of a linked list. So I'll assume without loss of generality that I have a single linked list, but you can do it for doubly linked list also. So here is my PTR to the list. Let's put some elements in there. I'm not assuming it to be circular, so there's a 0 element out here. And I put some values, let's say 25, 13, maybe 5, maybe 90. It's not important what the values are. But somebody says, I have figured out, I want to sort it, and I observe that 25 and 13 are in the wrong order. So I want to change it to look like, after some effort, it should become 13 followed by 25 followed by whatever. So what I am trying to do, I am trying to swap the values of the two elements, which are not too difficult. So now observe, if this is PTR or this is P1 and this is P2. Now let me take two arbitrary elements of the linked list. They may not be consecutive. This is some value V1 and this is some value V2. They point somewhere, we don't know. You have this P1 which is a pointer to this node and P2 which is a pointer to this node, and we just want to swap the values. So this amounts to swapping basically two ints which are situated in here. So how do you swap two ints? Exactly the way is what we will do. So we'll create a temporary variable, let's call it TMP. What is the type? Let's say int. I'm assuming these are all int, otherwise I'll change the type. I'll copy V1 into the temporary variable. I'll show you how to do that. Okay. Now once V1 is stored here, I can change this value. So I'll change this value to V2 and then I'll take this value of V2 and I'll change it to the value which I copy from here, which is this. So how do I write it in a programming thing? I'll use this short space. So P1 is a pointer to the first box, P2 is a pointer to the second box, and our job is to swap the values. So I take TMP, I have already defined. So TMP equals P1, you have to use this arrow to access this value and pick up the value, whatever the value field is, let's call it var. Okay, so this takes care of storing this. Then since I have stored the value of V1, so I can now do V1 equals P2 arrow val. Remember, val is the name of the field. The actual value will move and eventually I'll say V2 equal to TMP and I am done. So what did I do? I just exchanged the values. Now I do not know, maybe your friend does not want that. The friend wants that this whole box shifts. It's not merely the values which shift, but I want the boxes to move. That could be another way of swapping. I want to swap the boxes, not the contents. Okay, so I don't change the boxes here, I just swap their contents. So one suitcase had gold, the other suitcase had diamonds. In the gold suitcase I have put diamonds and in the diamond suitcase I have put gold, but the suitcases are in the respective places, right? If you want to do the other way around, then observe, I want to change this. So I want this box to go here and I want this box to come here. If you want to change the elements, the positions of the two boxes, it should be clear that I have to take these two pointers and sort of swap them, which also I can do. Whether you want to swap the boxes or you want to swap the values will depend on whether you want to use the value or the integers or you want to use the pointers to move them around. Yeah, both you can do depending on what. The last question which I thought I'll answer was about what is the advantage of using a header node. Now this has a deeper meaning, so let me explain this to you. Typically, remember, I have not elaborated in these lectures too much, but I have used this new every time in my code, which is the equivalent of malloc or calloc of C. Okay, this is a new of C++, through which you create. So let me draw these two parts of memory. One is heap for runtime or dynamic memory, and the other, let me call it static, which are your program variables. Okay, so where is the head? The head is typically somewhere here. The head of a list, when I say, it is actually in my steady memory or my static memory. Where is the list? The list is actually all on the heap. It may not be contiguous, it can be anywhere on the heap, and that is why it's a linked list. Depending on how it grew, whatever memory was available, it grew. So these are different part of memory and these are different part of memory. So head is the way I access the elements on the heap. If you know it, great. If you do not know, remember that these entities on the heap are supposed to be anonymous, which means they do not have a name, you only have an address. So you cannot call it X, Y, Z, head, tail, nothing. You can just take the pointer and keep it wherever you want. That's what we have done. So this is the pointer or address of the first element. The first element, one part of it is an address of another element in the heap, and so on, but there are no names to this. So coming back to the question, why is head important? Head is the only way to access the linked list which is in dynamic part of the memory. It is the only way. Let me use the word only very carefully. By some reason, by some mistake, if I do head equal to some 0, okay, which means a 0 sits here, it was there with this whole list has vanished and it will never be recoverable. And these are something like dangling pointers that somebody was asking on the previous. So head is the only way to enter the entire dynamic network that you have. So head is very important because head is in my static memory, or head is a variable that I control, but this is all this dynamic memory which is allocated, deallocated on demand by new malloc or equivalently by delete and the corresponding thing there is not is not accessible if you do not have this head pointing to the first element or the last element of your collection. Okay, I think I should move on. I'll move on to this part only because there are codes and problems. Now I'll be taking up applications. So firstly, I have planned to take one or two applications, but if somebody has an application which is very dear to his or her heart and wants some quick answers, you can ask me after I finish this. So there are a lot of applications. Most of them, once I'll discuss here, probably will use a queue or a stack. But you can use, but there are other data structures like graphs, trees, some of which I will do on in module 2, which will be happening subsequently. Okay, so here are some of my easy questions. The first question, which is known as, very popularly known as balanced parenthesis, okay, has an equivalent statement in many other forms. The question is like this: if I write some series of parentheses, could be one or could be more, suppose I write this and assume that there is something in between which I am not showing you because that is not relevant to this particular problem. So there are some things maybe between them, one or more integers. The balanced parenthesis problem says, for example, looking at the open and closed forms, every parenthesis has an open and closing forms. Okay. Is the expression balanced? Does it make sense? Because every parenthesis has a matching partner and the whole thing is correct. Okay. First, let me tell you some trivial counter examples that some simple ideas would not work. For example, looking at this, if I see there are 3 closing parentheses, there are 3 opening parentheses, that the match appears to be there, the same number of opening closing parentheses, they match, and therefore I can say it is balanced, maybe. The answer to that, you know, it is not, because it is important that an opening parenthesis comes first before a closing parenthesis. So this is well known, there is nothing new. So the question is, given an arbitrary expression like this which involves only parentheses of one or more kinds, there are more parentheses, can we figure out whether it is balanced or not? Having stated the problem, it should not be so difficult. So let's do it manually. So here is my opening parenthesis, great. Another opening parenthesis, great. Another opening parenthesis. I keep observing, there is nothing for me to object. Then comes a closing parenthesis. So when I reach the stage, we observe that this curly brace has not closed and something before it has closed. So this we don't like, because this brace should have closed before the corresponding thing has closed. So there is some problem out here. Okay, and then after that, so if I cite this as an error, I process this, I see one another closing parenthesis, I can say, okay, here is the matching partner, fine. I see another closing parenthesis, I should complain. This fellow has no matching partner. When it comes here, we'll have to say this fellow has no opening partner, because I don't see an opening partner at that level. This level should have been somewhere here, and so on. You observe that we write in case of languages like C, C++, we use these braces to denote scopes. You can have a nested if then else statement, and similar things may apply to these applications also. Has a properly inner if been closed before the new inner if has started? So I'll continue with this. It so turns out, if you look at this problem naturally, that a certain data structure just stands out as an ideal one for solving. So here is how it is done. We use a stack. Let's see why a stack. So I am going to use let's say this expression. The expression is not important. So I create a stack. I'm going to visually do it manually. I get a left parenthesis. If I get a left parenthesis, I know that I have not seen its right matching partner, so I should wait. I have no action to take. So this is the time I put it onto a stack. This is the decision. A left parenthesis, please wait till something has been seen. So basically push it on the stack. Keep a stack and push on it. I read the next symbol, I see another left parenthesis, I again push it on the stack by the same argument. Now I find a right parenthesis. If I have seen a right parenthesis, then everything up to the left parenthesis is the matching balanced expression. Thank you.